Konnichiwa minasan, and welcome back to Day 2 of TenguCon 2.0. I'm Yuna, your virtual host, and we are starting strong today. Kicking us off is the amazing Edmond Rogers, and he's talking about boiling the ocean, kernel data bus analysis. His whole idea? Forget just reading code. What if we could actually see what data is doing inside a running kernel, live? He's going to show us the tools and fun data visualizations that give us X-ray vision right into the OS core. How cool is that? Please join me in giving a warm welcome to Edmond Rogers.
Woo. All right, take it away, boss. All you.
All right, then. Good morning. I was wondering how they would translate polymorphic composition. How did they do? Is that what polymorphic composition looks like? Okay, I was just curious. So, this is DARPA project I am the principal investigator on in the projects in the I2 office at DARPA called Harden. And we have been engineering a tool that does what our young hostess said. I'm Edmond Rogers. I work at the University of Illinois, Champaign-Urbana, at the Information Trust Institute. And then we do research in critical infrastructure, and I lead a few projects for DARPA. And then this research was funded by DARPA, as it says in the words down at the bottom. This is foundational research, and I'll talk about this later. So in the beginning, there were PhD students. And Nathan Daughton-Hahn and Imani Palmer, who's my co-PI, were among a group of students that got PhDs at the University of Illinois about a decade ago. And if you were to go here, you could see this tool called Memorizer, or you can just Google it. And the keywords would be Memorizer and Linux. And so from the paper that's linked up above, you can see this idea about the internalization about how do you observe what is occurring inside the Linux kernel while a process is running, or what would it take to do that? And some of the secret pieces or ingredients in this are, if you use KSON, you can, in fact, make copies of every allocation, and if you were to build build off of the debug file system for the Linux kernel and assign memory, you can then keep a running list of all of the allocations that are occurring inside either the entire kernel or specifically a process, and I'll get into that in a minute. So nice graphic, and then, but you know, and overall, why we wanted to do this or engineer this tool is that poor visibility makes security difficult. And like I already said, what if we could provide a complete trace of all of the objects that are used in the kernel without losing any of that data? And then what could you do if you had a list of those objects? Well, I thought it would be a good idea to begin this as what it would look like if you were actually going to do this. So you want to open up a shell and go into the Memorizer file system, because there are like commands that you would need to run to send. We have in the debug file system different things you can do to clear out allocation lists and set up how much of the kernel you would like to record. And this is just a preview of some of the commands you might want to run, with the idea being that after a while you want to stop the process, and then these are the commands that you would use to do that. And then what happens is all of the list of all of the different allocations that run are then taken from the debug file system into userland so that you can then look at a CSV file which has all of the relevant information about all of the allocations that occurred during the recording. And the data looks kind of like this. So it's throughout the history of the engineering of this, this tool, we kept the same nomenclature here where the first address you see there, and maybe I'll just get ahead, and I provided a little better explanation on this slide where each of the 16-digit numbers that you saw is a pointer. And so on the left, the first entry is the initialization pointer, or the pointer that the process is using into the Linux kernel. Now, the mode that you run when you're running this tool is a forensic mode, because what we do is disable KLSR so we can see the actual pointer addresses. And this becomes important later because what we want to do is then be able to identify the function calls and the parts of the Linux kernel that are being used when the memory is allocated. And then if we go to the right, we have the data address of this particular allocation, and then the last line that is in bold in the first bullet is the free. And then we have other information in here, including if you see SSHD, we have the process name, we also have the process ID, and then we have a number of serial, there's a serialization of the data, and we'll see this later when I do the demo, where we account for every allocation in serial format. We used to use Jiffies, but discovered that Jiffies are not unique enough to make a list of all the allocations inside the Linux kernel. And then just some handy notes here. The ones that begin with 8 Fs are code pointers, and the ones that begin with 4 Fs are data pointers. And then I ruined this part of the conversation because I forgot I put handy animations in for that. So we have code pointers and data pointers. And then if you were to use a tool called ADDR to line, or address, I call it address to line, and then what this does is it will tell you the part of the source code that the particular memory address points to. So what I did was I handily changed each of the pointers that we see in a snippet of the KMap file to a different color, and then I just ran this command, and you can see that I can see the corresponding piece of C code that is in the Linux kernel and the line that that call came from. And then so each one of those colors is corresponding to which of the pieces of the Linux code. So it looks like we had a lot of skbuff in this particular command that we looked at. So, and a lot of the objects are referenced by multiple subsystems. And some are only referenced internally by one subsystem. And what we're looking at right now appears to be the latter case. The first pointer from the long KMap file I just showed is a point of allocation, skbuff.c, line 552. And then if I were to, if you see down here, I just went in and I take a look at this. This is the actual part of the Linux source code that address pointed to and what it does. And we can see that if you know C, you'll see what it's doing. And then the third pointer from the long KMap file is a point of deallocation. So what we do is when the memory address is allocated, we make a notation of it and build a list. And then when it's deallocated, we then make an entry in the debug file system. And then as the tool began to get engineered, we discovered that we could do this for longer if we were able to stream this, the deallocated data, the IPs that had been freed. We can stream that data out. We could run the tool for a longer amount of time. Of course, this is after we spent 2 years getting the tool going from the first time we actually started an application called Q Ground Control. It's an avionics software for like flying drones around. And normally it takes 5 seconds for the screen to open up when you start the tool. The first time we were able to successfully record that in the kernel, it took 2.5 hours for the screen to come up. Now we can do it in real time, and this is 3 years into the project, and we'll see this in a minute. But I really felt it was like maybe just an introduction into what are going to be some of the things you're going to see flying around the screen here in a minute might make a little bit of better sense. And then like I said, the pointers in the shorter line represent locations where the pointer is dereferenced or the free. And then we can also look those things up, corresponding colors, and then I'll likely end up sharing the slides with Tengu so that if you wanted to go back through, you could actually follow through and see that these were from the IP addresses that we had gotten from the tool before. And then we also have, and then I've got a slide about this later, so let's just move on. So what do you do with this data? So what we want to do is look at security risks by looking at this low-level data with directed acyclical graphs and or DAGs. And then why do we want to do this? We want to analyze exploitation. We want to assess pre- and post conditions of the exploitation, determine any dependencies. So say you have an SBOM and you have a piece of open source software and you actually want to know what dependencies and what libraries does a piece of open source software actually use. With a tool like this, you can actually perform that forensic investigation of a running piece of software. And, but it's been notoriously difficult to retrieve, store, or assess any of this data because there's a lot of it. And a lot of people get mixed up between, this is not the actual data, because that's what, reverse engineering tools do this. You have IDA and these other tools that can provide you with a different look from user land. This is a list of the allocations based on the IP addresses of the allocation. So I just said a bunch of this stuff already. And so what you can do is you can make graphs. So a lot of these graphs came from the PhDs that were minted out of UIUC. And then if you go to the Fierce Lab site, this is actually online. And I won't tempt the demo gods to go to the site right now because I have the tool running in the background right now. But you can build a heat map, and then you can also build like what pieces of code talk to what pieces of code. And then when we started to get more information about how programs were running, we were able to get a little more sophisticated and use things like directed graphs to show, excuse me, I can't see my own screen right now. So these are, what we did was we broke out a listing of all of the allocations based on just directory structure of the Linux kernel. And then the numbers represent the number of times they were observed in our observation of the Linux test project, or Linux test, the Linux test project. So, and then we zoom in a little bit, we can see all of the interdependencies between just the file systems. You got MM and FS and lib and security, and I think net is in here as well. If you look down here, there's got to be net somewhere. And this is the Linux test project. And then what we could also do, or did, was look at the Linux test project and then dump this in D3, which is a graphical library. And then and these are not the directory structures. These are the actual, just the C files that are used in a process that's running in the Linux kernel. And then we look at another view using D3 where you have a representation of the different file structures. And then with D3, we can build little cool movies and show the interaction of objects and what they connect to by clicking on them. And then how we derived all of these interactions was from just observing allocation data. But that's kind of like an introduction as to what you're getting ready to look at. And then the tool from the PhD paper is called Memorizer. And the way it stands right now, it's been engineered as a proposed Linux kernel feature. And it provides deep dynamic visibility into the Linux kernel. And then recently, as of, I think it was version 27, maybe 26, the biggest problem we had with Memorizer was that we had to lock everything into one core. Because when you start to look at how individual cores communicate with each other and all the caching that is involved, you'll run into a situation where you end up copying yourself. So how the PhDs, to get their PhD, did to remedy this was that we just have to nail down to one core. So everything needs to run inside one core. But a couple of versions ago, we're having a meeting, and if you use the task set command, you can nail processes into one core. So we said, if we nailed the Memorizer process and the program under test into the same core, we could still have the rest of the cores to operate the file system and get a performance improvement. And we were able to improve performance by 1,000 times by doing this. So that is, kind of looks like this in a screenshot. But if I did this and this, pardon me, and then, so this is Hyper-V. And then this is Unix. It's a Ubuntu running in Hyper-V. And then, so inside this Ubuntu, I have Virt Manager, which is a hypervisor for Ubuntu, or any Linux, I would guess. And down here, we have a screen, and you can see from the, I wonder if I can make what I was talking about earlier, we have the IP address, and we have the PID, and we have the data address, and we have the size of the allocation, and then you see we have the serialized. The four-digit numbers are the time that the allocation, in terms of the serialized counter that we keep from the beginning of this, and then the number next to it is when it was freed, and then we have the free, and then we have allocator information, and then we also have the name of the program that was running. So the host OS is receiving this data from inside this virtual machine that's running in Virt Manager. So we have another virtual machine running where what you're seeing here that's highlighted in white are the live memory-disabled allocations that are being observed inside the debug file system right now. And then over here where you see this top that's kind of been shut down, I'm going to go ahead and do a clear on this screen. So, and then, so if I do echo $$, you know, the PID of this bash is 5072. And then if I come over and look at dmessage, I see that I've nailed process 572 to CPU 0. And earlier, I had limited process. It's like an eye chart for me, too. 5061 to core 0, because that's the process that is streaming data back out to the host OS. And then, so if I come back into the shell, I can now run any command and see the corresponding allocations. So what's a good command to run? Anybody know a good command to run? Hi? Anybody? Walmart. Who am I? Did I hear correctly? Who am I? Okay. Who am I? Boom. OS boxes. And we see some stuff came up out here in the main OS where we caught that. And then you could do other things like, I can do, am I in the right directory to do this? I can start avionics software. So while the avionics software is starting, we can see that, oh, there it goes. And I don't know if this is actually online. I tried to go online, but I don't know if it's actually working, so we'll see. So you can see that there are a lot of allocations occurring right now as this software is open. And then I'm going to move this over to the right. The demo looks a lot cooler if you have a bigger screen. So I'm going to move the running software over, and we can see down here, I'm going to minimize the stream right now, the VM that's streaming right now, and show. So these are the live allocations that are occurring right now. And then if I were to go in this VM, I could show you that so I've got 16 cores in this VM. We can see that some of the cores are very busy. And we see the network, the corresponding network traffic, which is probably hanging around 5 megs per second of data coming into the live stream. And then if I want to come back over here, I can connect back into the, why is it doing, is this the wrong one? It's the wrong one. That's a different one. So come in here, we're back where we were to the, and then we can see that we've got a lot of frees that are being streamed out, and then I can also run from the perspective of this internal VM and show that I've got just 4 cores in this VM, which is inside the 16 cores in the other VM. And we can see that, I don't know if you can see that okay, in the top we have the one core is very busy right now because it's trying to run the avionics software and stream the data out at the same time, and it's managing. But if I do this and then come over here, I'm going to pull this way. I want to make this smaller or move it over here so that you can see the processor. Now I'm going to shut down the avionics software, and then now I'm going to watch the processor drop down because I'm not running the software anymore. And then we can see that eventually the allocations that are in back pressure right now inside the debug file system are finally going to, we're going to see the streaming down here on the left slow down, and then we're kind of back down to a steady state. And then, so I wonder if we're online. Let's see. I don't know if it's going to make it all the way out. It was working in the hotel, but it may not be working here. There's only one way to find out. Let's start Firefox. Firefox is actually less heavy than the avionics software. It should come up here in a second. So we were only able to actually do this and start up Firefox and show the allocations maybe in the last, maybe version 28. And then if I was online, I could then go into and stream a YouTube video. I'm going to go ahead and shut that down now, and then everything will slow down again. And then while this thing is calming down, what we can do is come back in and see that, I think I've got another. So the data that's being streamed is in the host OS, it's in user local Tengu directory. And so if I did, let me see if this is going to work. Control Shift. Can y'all see that bigger now? Is that, yeah? So if I do ls minus lrth, let's see how much. So in this demo, I just streamed 599 megs of allocation data. So let's do wc minus l. Word count minus l will give me the number of lines of data that I have in that file. So I'll do that on live. That is 5,096,420 allocations. And then let's do, well, we got the tail over here. And the file kind of looks like this, right? This is I was live tailing the file in the other screen. There it is. So the file looks like this. I can go through and show you the thousands of lines of code, but we have the IP address and the free and this kind of thing. We'll just leave this running and get back into the slides. So the demo worked, Kamal, I guess. Did it work? Yeah? All right, let's get back in here. And then I think, so this is a movie of what it looks like when you start, I think I do Firefox streaming in this one. And then this version is the current version that's in development. What we did was, if you look at the stats in the left of the screen, we have a richer set of running stats so that you can see, if you look in the top, there is this idea about current. And then as you see in the demo, as I start to do things, there's a 0 where all the white stuff is right now, and that so what I'm doing with this command in the left of the screen is constantly tailing the stats file. And here I am, I've started Firefox, and then I'm going to go out and go to YouTube, and you can see down in the bottom left, the data is streaming, and then if you look at the current line, I see that I am currently 400,000 allocations behind in the stream. And then as Firefox starts to load the video, we see that the number of allocations behind in the live stream is up to 700, 800,000 now. Skip through the ad like you do, right? And then we notice that not only is my application the truck driver that is live streaming is also in a traffic jam as well. And then now we're up to 900,000 allocations that we need to stream, and then you shouldn't push on the podium while you're doing this. And then, so mission accomplished, and then so we can also see that Memorizer sends messages into dmessage so you know that everything is going on. So like if it crashes, it'll send a message, this kind of thing. And then we see the number of current allocations is now going down a little bit, starting to get to a little bit of a steady state. And then also, I just highlighted in the video, there's a memory usage statistic. So right now, there are 30 gigs of memory that are being used to store the allocation data that hasn't been freed yet. And then here we go in a minute. I think everything should kind of peter out in the video here. I'll shut the Firefox down and we see the number of allocations. Go back up again as things get freed. And now we're coming down back to 0. We've caught up. We've gotten all of the allocations that were used by running Firefox back into the KMap file in userland. So this was my backup demo, but I thought I'd show it anyway because it shows Firefox streaming live video. You know, for us, it was a pretty big deal to get there from spending 2.5 hours to watch a program start that's supposed to take 5 seconds to being able to like stream video and see all the allocations running. So let's go back to the slides. So this is a link to the software that I used in the demo. It is available on GitHub at this location. And this version includes the SMP add-on that we did in version 28. And again, you can stream data out from kernel land into user land and then use that data for many interesting things. Like we talked about before, you can use it for possibly feeding machine learning, outlier detection, baseline generation. So we have folks that are using the idea about, I want to be able to baseload what an app looks like and then when it deviates from that. And then I kind of started up this Q ground control software already, and it's drone control software, and we use it in our avionics test bed on the DARPA project. But you know what we decided to do, and then if you look at the containers here, is you'll see a list of. Let me go back in here real quick and take a peek. I've got a bunch of different VMs here that all have CVEs associated with them. So what we did was, and then there's a slide about this later, but anybody know Google Project Zero Kernel CTF? You know, they've got great write-ups where they have a tainted kernel, and then they have the proof of concept, and then there's like a 40 or 50 page write-up about everything that does. So what we decided to do was we followed the LTS kernel with Memorizer. So I think we're at 6.6.51 right now. But we backported so that we had exploitable kernels and then use the POC to call out a rootkit that we had a student write that would then send packets out to make the drones land in the simulation. So that way you could do things like, if we go to, am I in the slides? Oh, I'm showing this stuff. So like each one of these is a different CVE. So if I were like to go to this screen, I have there's a different Linux, and then I had the exploit sitting on the desktop. I can run the exploit and get the chain up, and then run Memorizer and see the exploit. And then that kind of looks like, in data analysis, and then, so where I ran the demo from was CVE 0193 from 2024, and, but you got a demo of that. And then what we use in data analysis, and this is available as well in the memory analysis toolkit, is mainly use Jupyter Notebook because our customers like to get the Python in Jupyter Notebook because there's lots of comments and it explains everything that's going on. because it makes interesting analysis results. So from CVE 0193, 2024, what time is it right now? I didn't look, I'm sorry. Well, I'm doing pretty good, aren't I? Because I've got about 10 minutes of things to say. So the process exploit_RMIT, it has over 20,000 unfreed allocations. And CVE 2024-193 is the Linux kernel vulnerability in the sigqalloc function. And the flaw allows attackers to trigger uncontrolled memory allocations. So if you're the attacker and you run the POC and you just spray out, I don't know, what was this, 20,000 allocations, if you happen to be inside the kernel looking around, it's very noticeable. What you can do is build a data analysis suite that can provide fingerprints for certain behavior that within your own threat model may not be something that you would want to allow. For another example would be, here's a spike isolated in signal.c, and I think this came out of a rootkit. The exploit RMIT process exhibits extreme spikes, and then the massive spike for the exploit indicates it's just hammering the kernel. And there's a lot of background information there. But these graphs were driven by Jupyter Notebook and customized Python that is available in our website via open source. And I think there's one more. And then, so this is a list of all the system calls. And then again, we can see that the system call CSL ACT_find makes the most amount of invalid freeze. And then we can see that aberrant behavior inside the kernel sticks out, especially if you have a tool that can bother to look. The tool is going back in time. I can remember in the 90s when TCP dump first came out, and we're like, oh, this is cute. We're able to see the packets on the network, but what could come out of that? And then people always ask me, well, what can you do with this? I said, I don't know what you can do with this. I just know that I can look now. And basically, it's TCP dump for the kernel. And certainly, there's a lot you can glean from the memory allocations that occur inside the kernel. And, I've done what I can do in the, I don't know, some 39 or 40 minutes I've already talked, but the whole idea is just an introduction to the idea that, yes, it is possible that you can get a running list of all the allocations that are happening inside a process that's running inside the Linux kernel and do data analysis in real time against that to provide for a forensic look at system calls that would then allow you to do things with things like eBPF filtering to provide either canaries or checkpoints for aberrant behavior that you wouldn't want to tolerate inside your own attack surface or threat profile, however you want to determine that. Because if I recall, I might be done. No, forgot about another thing you can do is if you know somebody who knows game engines, actually put the live stream in a game engine and rotate that thing in 3 degrees. And if I'd remembered to move the video, I'd be able to show it to you right now. Maybe catch me later and I can show you the video. But we also have code that allows for real-time visualization of allocation data so that you can see those screens. And then one of the things that we're working on is how do you visualize the order of magnitude and difference of the pairs of IP address versus process ID, when you have, I don't know, we have 500 million allocations, and there's really only 10,000 pairs, and then really there's only a handful of things that is most of the data. So you have these really giant, more than exponential logarithmic blobs of data. How do you visualize that? And so it's an ongoing research problem for us. And then now we can get up under the rug and say thank you for listening to me babble at 9 o'clock in the morning. Does anybody have any questions or is... Okay. Behind the mask. Well, this is a heat map of exactly what you just said. So this is a running number of all the allocations that were observed in the Linux test project. And then I could also do that individually for a process as well. One of the things we did, we had an experiment where you can actually get in and run. I did an experiment where, and I've got a different set of slides, catch me later, where I take, I have a shell running that's doing like, I'm in less on a file, and then I open up another shell and I do a kill all less. And then I can actually show the sig, the everything. It's all in there. And then I use Cytoscape to do an analysis of that, and so we can see these kind of things. But then again, in 45 minutes, you can only do so much. But yeah, the answer is yes. That's the cool thing about it. I mean, it's all there. And then the other thing is interesting is I think there's about 13,000 addresses in the Linux kernel. How few of them are actually used, it's just the volume of the number of allocations of certain things. And then like the graphical operating system, because there's a mode where you can just record everything. And I can tell you right now, systemd and snap and GNOME are responsible for 80% of the just bloat. I mean, like, Ubuntu is becoming Windows-like. And then I forgot to mention that while you're doing all of this, I don't recommend doing this from Windows unless you have to present, because I am using 105 gigs of RAM right now. Yeah, it's fine, because I can still run Fortnite while I'm doing all of this. So, this machine has 32 cores, 128 gigs of RAM, and, I wanted to be able to, because one of the things is when you have an NVIDIA GPU in Ubuntu, and then you alter the kernel, the HDMI port doesn't work reliably, and then it's not really easy to rock up and do a presentation. So you spend your time learning how to run Ubuntu inside Windows. But, you know, you can do all of this natively in Ubuntu, and then you can shave off. I mean, I'm spending 60 gigs just to do the demo because, you know, Windows uses a lot of RAM as well. It's natively in Unix, it's a little more elegant, but not for our demos, yeah. But that was a great question, thank you. Hopefully that, you know, I mean, that it's all there, and it's also very interesting data. And then, like, if you're building an S-bomb or this kind of thing, it feeds right back into that as well. And I'm probably getting the hook now. And I'll be here all day, so I need to step away so we can let the next speaker talk. Is that right? Come on.
Yeah, afraid we're out of time for questions, but
No worries.
let's give another hand to Edmond Rogers.
Thank you. Let me get this.